Okay, so far we have seen how 5 different types of clustering work, right? We've seen k-means, hierarchical clustering, we've seen Gaussian mixture models, spectral clustering, and density-based clustering, dbScan. We have seen how the algorithms work, how these different algorithms separate points into clusters. Now, as usual in this course, all these things happen within packages that we are going to be running. You don't need to write that code yourselves, right? And so in this section, we're going to be seeing the different packages that you can use, some of the different packages that you can use in R to run clustering, and a few examples, very simple examples of how to, do clustering in R. There's different packages. I recommend, for example, for k-means, using either k-means or PAM. For hierarchical clustering, I recommend using hclust, which basically depends on a different data frame, which is this data that computes the distance between all the data points so that we can then, remember, cluster them together from being each point an individual cluster all the way up to being all points within one cluster. For density-based, I recommend using either FPC or dbScan, and we'll see examples for k-means, hierarchical, and density-based in this class. And then for spectral, you can use a package called spec, where you need to specify, remember in this case, we need to specify the number of centers or the k-value. Remember that here, the idea is that the first k eigenvectors is basically the number of components in the graph. So it's, sort of the number of clusters that you want to identify. And then Gaussian mixture models, I recommend using mclust, and it basically evaluates, like different clustering, number of clusters from 1 to 9. I'm going to be showing very simple examples for k-means, hierarchical, and density. I really encourage you to use and to test all the different packages, and you will be asked to run different clustering tasks, as part of your homework. So make sure that you play with these different packages. And I've added also here more information. Every time you use a package or library in R, there's, software behind that library. Again, if you're running k-means, somebody in the community actually implemented the k-means algorithm that we described, and that's the library that you're using. And every time you use one of those libraries in R, there's a file, a PDF file explaining, the different parameters, the meaning of those parameters, variables, and so on. And so these are the PDF files that you can also check to understand better how to run many of the libraries for the clusterings that we have discussed today. And I'm going to start with a very simple example with k-means clustering. We're going to be using a data set that's embedded in R in one of the libraries that R has with different types of data sets. The data set is called US arrests, and this has arrest information per 100,000 residents from 1973. The arrests are characterized by either assault, murder, or rape, and they are divided by states. So we have information for 50 states. We also have, as another piece of information, the percent of population living in urban areas for each of the 50 states as well. And so the idea here is basically, can we use, in this case, k-means clustering to identify how the different states are clustered together based on these arrests information, as well as on the percentage of the population living in urban areas. And so let's go on with R. Let me move this here and open R. Okay, we're going to be using a couple of libraries. So we're going to be using the Facto Extra library, which contains, a set of data sets, including the US arrests that we're going to be using. And I'm also going to load the nbclust library that we will be using as well. Then the first thing that we do is load the US arrests, okay? So, and we are gonna basically load it and then normalize the data set, okay? So generally when you run clustering methods, if the, the different variables for each data point have different dimensions, clusters might be dominated by just that one dimension. And so what we propose here is just we normalize everything so that the values are sort of more similar, across. And so what you can see here, for example, if we check the data frame we've created, these are normalized numbers. And so, the clusters that we will identify will not be, say, dominated by any one of these features, but rather, by all. So, if we say here US arrests, and we view that data, you can see here basically these are the raw numbers from the data set. So you can see that the numbers in terms of, assaults are much higher. And so, if we don't normalize, basically the clusters could be dominated by that one feature. So that's the reason why we normalize. Okay, and once we have this data normalized, we can use the k-means library to compute k-means. And we need to specify the data set that we use. So the set of points that we're going to be using to identify clusters. We need to specify the number of clusters. In this case, we're saying let's start with 2. And then the nstart command is critical. What the nstart command does, if you remember when I was explaining k-means, I was saying that, because of the way we choose the seeds randomly at the beginning, the results that we get might be different because, if those points change, then how we compute the distances to those centroids and then how those centroids are recomputed might change. And so the way we work with clustering is that we run k-means many, many times, and then we look for sort of the best result. And I will explain in a second what that best result is. But, for now, let's say that, k-means is a package in which you specify the data set, the number of clusters, you run it 100 times, and it outputs basically the best, clustering. And so we can then visualize those clusters using fb's cluster command, where we specify I want to visualize the output of the k-means, k2, and the original data is, this data set. So what do we get in this visualization? What you can see here basically is that we asked k-means to identify 2 different clusters based on the normalized arrests variables. And what you can see here is that, 2 well-differentiated clusters have been identified. Now, this is just the best of the 100 runs that k-means has done, okay? Okay. So, this is sort of the simplest version that we can run for k-means. Now, what happens is that we started running k-means with just k equals 2, and that's a good starting point, a good intuition. But generally, the way we identify the number of clusters that we want to input into the k-means algorithm is by using the elbow method. Okay, so let me explain you the elbow method by showing you this visualization, and then because I think that it's going to be easier. So I'm going to be using the again this library, the fv's nb classed. Okay, and then I'm going to be using the dataset df. I'm going to be using the k-means algorithm, and I want to use a method which is called within sum of squares, within cluster sum of squares. Okay, so let me explain you what this means. So what we are computing here, it's basically, for different number of clusters. So we are considering running k-means with different numbers of clusters, and for each set of number of clusters that we are considering, we are computing the total within sum of a square. So say we are working with 2 clusters. For each of those clusters, we compute the distance between points in each cluster, and we average, okay, and that average distance is 100, average square. If we consider 3 clusters, we compute the average distance between points within each of these 3 clusters, and the average distance is around 75, and so on, right? So we are evaluating how dense or how close-knit different data points within the clusters are for different k values. And that's exactly the representation that you see here. Now, the reason why this is called the elbow method is because we are trying to look for that point where this plot breaks in the sense that there's like the largest change in terms of these sum of distances, right? We're looking at the place where the number of clusters that we consider really decreases a lot the distance between the points within each of the clusters. And by looking at this plot, I'd say that that value is 4. Okay, and so then rather than running k-means blindly with different numbers, we look at this plot and we say, okay, so let's run k-means with basically 4 centers. And so we can do exactly the same thing. We can run k-means again, right? But in this case, we're going to run k-means with 4 different centers instead of 2. And we're also going to run it randomly 100 times and pick the best one. And when I was saying before that the best one, you know, is going to be, and that I will explain in a second how the next one is computed, is exactly using this type of approaches. So k-means runs, you know, identifies 4 clusters 100 times and then identifies as the best the one that has the smallest within cluster distance between the data points in each cluster, okay? And we can again, you know, basically visualize this, but in this case we'll get, instead of 2, we will get 4 different clusters. And, you know, understanding, we could look at, you know, other types of features from those, from these different states. We could look at, I don't know, like different socioeconomic characteristics, or we could look at different legal frameworks in each of those states and try to understand better what these clusters are telling us. Okay, so this is for k-means. Now we're going to be using exactly the same data set, but running hierarchical clustering. For that, we need to load the library cluster. Remember to install the packages if you have not installed them. And again, as we explained in the theory, the way hierarchical clustering works is that we start with every single data point being a cluster, and we start putting the points together based on distance. If 2 points are similar, we cluster them in the same cluster. You know, the 2 points that are the most similar are clustered together. Then the 3 points that are more similar, the 4 points that are more similar, and so on, until we get this just one unique cluster, right? And so the first thing that we need to do is compute the dissimilarity matrix, basically compute what's the distance between the different points that we have in our data set. And what the distance function is doing. We're basically inputting the data frame that we have, and then we are telling the library to compute the Euclidean distance between all the data points that we have, right? So if you look at D, let me go up. If you look at D, what you can see here, this is just the distance between the Arizona and the Alabama vectors. So you have these 2 vectors, each with 4 variables. You compute the Euclidean distance between these numbers. Okay, and this is exactly the distance. The larger the distance, the more disparate, the more different the statistics for those 2 states are. Okay, and once we have this distance matrix, we can actually run the clustering. So I'm going to call the output HC1. We will run this hierarchical clustering hclust. We are using this matrix distance, and the method will be complete. Okay. And then to plot the result, to plot the actual dendrogram, you can use this command here. Okay, and what you see here is basically the dendrogram, right? Again, we start with every single state being a unique cluster, and you can see here how states are put together in pairs, then in 4s, then in 8s, and so on, right? And so basically this is where we need to sort of interpret where do we cut, right? I mean, here we have all the different combinations. If I cut here, I'm going to have 2 clusters. One cluster is going to be this big thing here. The other cluster is going to be this big thing here, right? If I cut here, I'm going to have 4 clusters, and so on. And so, you know, this is what you obtain here with the hclust command, and the distance between the data points is the whole construction of going from data points being individual to having this one unique cluster. And then, you know, you basically have to identify where is it that you want to cut. Okay. And then we're going to move to density-based clustering. That's the last example that I want to talk about today. And again, I'm not giving more in-depth examples because you have to run exactly these type of things for your homework, and I want you to, as part of your homework, to delve into these packages and to understand how they work. So, you know, for density-based clustering, we're going to be using a package which is called FPC. There's also another one called dbscan that you can also check if you'd like. And I'm going to be using a data set, again, from Facto Extra, which is called multi-shapes. Okay, and basically these are just groups of points with an X and a Y value, okay, that have different shapes in a 2-dimensional space. And basically, we want to use dbScan to identify, different clusters within this data set. So the first thing that we do is that we load this multi-shapes file from FactoExtra. Okay, and then we basically take from multi-shapes, we take all the rows and basically only the first and the second column. So if you look at the F is just a set of more than 1,000 different points where this is an X value and this is a Y value. So if you think, about an XY axis, you are representing, these different XY values. And so now we want to compute clusters for these shapes. What do? We load the library FPC. And then we set a random seed as usual. And what we do is that we run the FPC package and we specifically call dbScan, okay? And for dbScan, we specify that we want to compute, the different density-based clusters using data from the data frame that we have created, basically the data frame that you see here with all the XY data points, right? And then with density-based, remember that we need to specify the epsilon value and we need to specify the minimum number of points, okay? Remember that basically the minimum number of points is the minimum number of points that we are requiring basically a cluster to have in its neighborhood, or a data point to have in its neighborhood, and epsilon is sort of the minimum distance that we are requiring, okay? And so, if we do that, and we can check the structure, the output of this dbScan function, basically what you can see here is that we have 5 clusters, and it's telling us how many border points we have there and how many total points we have there. But this zero cluster, what this zero cluster means is basically the outliers. These are points that have not been added into any cluster. Let's visualize this because, clustering is much easily explained when we visualize clusters. So we want to visualize the output of db, and the data that we are using is the F. Okay, so what do we see here? So these are basically all the data points that I was talking about before, all the XYs, right? As you can see here, our input data is just a bunch of XY values, right? And what we want to do is identify different clusters. So what dbScan has done is by specifying a minimum number of points as 5 and the epsilon as 0.15, these are the 5 different clusters that we have identified. And these points in black, if you count them, they are exactly 31. These are the outliers that we see here, okay? Okay, so far when running dbScan, I've just been saying, okay, you need to think about the minimum number of points that you want to use. You need to think about the epsilon that you want to set up. Again, how many points do we require for a minimum number of points that we require for a cluster to be considered a cluster? What's the distance between these points, right? And we have just assumed that choice, but a choice of the minimum number of points is relatively obvious. I mean, if you know your data and you know what types of clusters you are looking for, you could set up sort of that minimum number of points. For example, say you are clustering states, so you could say, okay, I just want to identify clusters that have at least 10 states, for example. But the epsilon value, approximating the epsilon value, is not that straightforward because it's not so easily interpretable, right? And so the idea is, how do we come up with an epsilon value that is right? And the approach that we use is extremely similar to the ELVO approach that I just explained for the k-means. So how does it work? The idea is to basically, since we have this minimum number of points, is to compute the average of the distance of every point to its k nearest neighbors. So again, given any point, look at the k nearest neighbors and compute the average distance across all points in your data set, okay? Then we plot those k distances in an ascending order. And we look exactly at that sharp change, at that elbow, sometimes it's also called a knee. And that's going to be the optimal epsilon value, Okay, so let me show you how we can do this in R. It's very straightforward. So we're going to load the library dbscan, and then we're using dbscan, specifically the KNN this plot function, and we're saying use the data frame df that we've been using, and we're going to use the minimum number of points that we are requiring is 5, right? And so what you can see here we basically see the average distances between any given point and the 5 neighboring points. And what we're looking is basically at a point where there's a knee or an elbow in the plot, and that will be the epsilon value. If you think about these, 5 nearest neighbors distance, what this is representing basically is the epsilon value that we want to take. Remember that mean points is the minimum number of points that we want in the cluster, that are points that are reachable from the centroid, and then the epsilon is the radius. So if we're looking at sort of the average distance between these 5 points that will find this break point, that's basically the radius for those mean points, right? That's the epsilon value that we are looking. And so in this case, that break point will happen sometime somewhere around this 0.15, which is exactly the value that I had set, in the example, because I already knew that that was the best value. But if we were kind of doing it backwards, right? I mean, if you were to do it from scratch, then you basically need to run these where you try to identify you figure out or reason about the minimum number of points, like for example, how many states do you expect per cluster, then you run this plot, identify the epsilon value, and then you can basically run dbscan and identify what the different clusters are, for example. Or in the example of these points, x and y, you first identify what's that value for epsilon, and then you run dbscan with the number of clusters that you're interested in and with this specific epsilon value. Okay, and the upline command is just to basically draw a line at 0.15 so that we can see that that could be the breakpoint. You can test that. And I will see you next week, where we will be talking about analyzing model performance.